Chapter 19 Model Evaluation Part 2. The evaluation metrics introduced in the previous chapter include shortcomings and trade-offs. To overcome these problems, several more balanced and more complex indicators have been proposed. In this chapter, we will learn those advanced metrics. As we have seen, as recall increases, precision decreases, and as precision increases, recall decreases. In other words, there is a trade-off between recall and precision. Let's take a closer look at this point. As an example, consider the following data. The pink dots represent positive cases, and the dark blue dots represent negative cases. Let's see how the recall and precision values change by moving the boundaries of the model that classifies this data. First, let's draw the boundary line at this position. Recall and precision are calculated to be 0.60 and 0.75, respectively. Next, let's move the boundary line downward a little. Compared to the previous case, the number of cases classified as positive has increased a little. In other words, this model is more likely to classify each case as positive than the previous model. In this case, recall and precision are 0.80 and 0.67, respectively. Since the model is more likely to classify each case as positive, the positive cases are less likely to be missed, resulting in higher recall. On the other hand, precision has decreased because the model is likely to classify true negatives as positive. Let's move the boundary downward further. The model is now further likely to classify each case as positive. Positive cases are no longer missed, and thus recall reaches 100%. On the other hand, the number of false positives also increased, and thus precision decreased further. Therefore, as recall increases, precision decreases. Looking at this figure from right to left, we can say that as precision increases, recall decreases. This trade-off occurs because if the model is more likely to classify each case as positive, false negatives will decrease and recall will increase, but false positives will increase and precision will decrease. Conversely, if the model is more likely to classify each case as negative, false positives will decrease and precision will increase, but false negatives will increase and thus recall will decrease. To address the issue of precision recall trade-offs, we can use a metric called F1 score. The F1 score is a metric that balances both precision and recall. F1 score can be computed as the harmonic mean of precision and recall, providing a balance between them. As can be seen from this formula, to keep the F1 score constant, when recall increases, precision must decrease. Conversely, when recall decreases, precision must increase. Thus, for the F1 score to be high, both recall and precision must be high. It's particularly useful when dealing with imbalanced datasets or situations where it is important to consider both false positives and false negatives. The F1 score is useful when you want to consider both false positives and false negatives simultaneously. However, it does not directly account for the class distribution. When dealing with imbalanced datasets where one class significantly outweighs the other, the F1 score may not reflect the true performance. Let's consider an example where there are 91 positive cases and only 9 negative cases. And the model's prediction result can be summarized by this confusion matrix. The model correctly predicts almost all positive cases, and most of the predicted positives are actually positive. So, both precision and recall are high, 0.91 and 0.99 respectively. Let's compute F1 score combining precision and recall. It is 0.95, very high. But let's focus on the prediction for negative cases. There are 9 actual negatives, but there are no predicted negatives. It means that the model missed all the negative cases. So, specificity is 0. As we can see, for such an imbalanced dataset, F1 score can be a misleading matrix. Another metric that balances between multiple metrics is geometric mean of sensitivity and specificity, often called G-mean for short. G-mean is the geometric mean of recall and specificity. Remember that recall is also called sensitivity. G-mean is a measure of balance between classification performance on both the positive and negative cases. It tries to maximize the accuracy of both positive and negative classes while keeping these accuracies balanced. A G-mean value of 1 indicates perfect balance. A G-mean below 1 suggests an imbalance favoring one of the rates. Lower G-mean values indicate that the model's performance is skewed toward either positive or negative predictions. Let's compare the results of two classification models. In the first example, the model achieved high recall, 0.8, but it is low in specificity, 0.22. It means that this model correctly predicts positives, but is poor at predicting negatives. When we compute its G-mean, it is 0.42. In the second example, both recall and specificity are moderate, 0.6 and 0.56, respectively. In this case, G-mean is 0.58, higher than the first example. It means that, compared to the first model, the second model's prediction performance is more balanced for both positives and negatives. So, in terms of G-mean, the second model performs better than the first model. F1 score and G-mean enable us to obtain a holistic view of the model's performance, rather than relying on a single aspect of classification. However, they also have pros and cons. F1 score combines precision and recall into one matrix, so it is useful when you want a balance between precision and recall. However, F1 score may not be as interpretable as simpler metrics like precision and recall. Moreover, it is not sensitive to the distribution of actual positives and negatives, so it can be misleading when positive and negative cases are extremely imbalanced. Therefore, F1 score is useful when there is an uneven class distribution where positive class is the majority. F1 score is also useful when false positives and false negatives are similarly important. G-mean takes into account the balance between performance on both classes, so it is useful for imbalanced datasets. However, it is less commonly used and so less understood. Moreover, It may not fully convey the trade-offs between precision and recall, but it considers only recall and specificity. G-mean is useful when the balance between sensitivity and specificity is important. It is also useful in imbalanced datasets where the cost of misclassification is different across classes. The MCC is an alternative metric that addresses the limitations of F1 score and G-means. MCC considers all four elements of the confusion matrix: true positives, false negatives, true negatives, and false positives. MCC can be computed by this formula. MCC produces a more informative and truthful score, especially on the imbalanced datasets. MCC ranges from -1 to 1. MCC equals -1 means perfect disagreement between predicted class and actual class. MCC equals 1 means perfect agreement. A positive MCC indicates better than random performance. Let's see the example I saw in the slide of limitation of F1 score. In this case, F1 score is very high, but specificity is very low. If we compute MCC for this case, it is -0.03, very low value. The confusion matrix provides a comprehensive snapshot of a model's performance, breaking it down into the basic components of true positive, true negative, false positive, and false negative. From this, we can compute a variety of important metrics such as accuracy, precision, recall, specificity, F1 score, and G-mean. These metrics provide detailed insights into different aspects of the model's performance, including its overall accuracy, its balance between sensitivity and specificity, and its precision in predicting positive cases. By analyzing these metrics, you can get a nuanced understanding of a model's strengths and weaknesses, which is crucial for improving model performance and making informed decisions. We have seen performance metrics that are used when we apply logistic regression models as classification models. Some of you may wonder that how model evaluation by metrics such as accuracy and F1 score differ from the evaluation using log likelihood and pseudo-determination coefficients, which were discussed in the previous chapters. Log likelihood and pseudo-determination coefficient evaluates the logistic regression model from different aspects. The log likelihood and pseudo-determination coefficients are suitable for evaluating the goodness of fit of the model and its explanatory power for the data, indicating how well the model fits the distribution of the data. They are useful in assessing the strength and direction of the impact of the predictor variables on the dependent variable. On the other hand, metrics such as accuracy, recall, and F1 scores assess how accurately the model predicts classes. These metrics directly measure the degree of agreement between actual class labels and the predicted labels. These types of evaluations are not the same thing. For example, consider a logistic regression model predicting the probability of 3 samples being positive. Suppose the observed values are 1, 0, 0, and model A predicts the respective positive probabilities to be 0.6, 0.4, 0.9, and model B predicts 0.4, 0.6, 0.0. If we set the cutoff value to 0.5, the labels for the dependent variable predicted by each model would look like this. Model A correctly classifies 2 of the 3 observations, while Model B correctly classifies only one of the three observations. Therefore, when evaluated by accuracy, model A is better than model B. Next, let's calculate the log likelihood of each model. The larger the log likelihood value, the better the model. So, model B is better than model A in terms of log likelihood. The reason for this difference may be that model A reflects the data to a lesser extent than model B because the predicted probability of the third observation deviates significantly from the observed value. This example indicates that the log likelihood and pseudo-determinant coefficients evaluate different aspects of the model from the accuracy, recall, and F1 scores.